equation. Let me pick up y equal to a cos kx minus omega t. Immediately we know how to calculate the pressure wave. So how do we calculate pressure wave? Excess pressure wave, that should be equal to minus b dy by dx. Please do remember, this is very important for you. You have to remember this. If you know displacement wave, can you bring the pressure wave by using this formula, excess pressure wave? So this will become minus b, derivative of this minus a sine minus ak what is this BAK? We'll call it as pressure amplitude. Now what you have, this is y of x here. So this is a displacement wave. And this is a pressure wave. Okay, just do look at this one. Let's plot these two. Then we'll see what we'll get it. We will try to we'll try to learn something from these equations. Let's plot them. I need some space. Let it be like this now. Okay, let's plot y of x graph at t equal to 0. So I think now we are very good in plotting graphs. All the things, even the energy also, I'll try to explain here only. Even the energy also, since now we know energy also. Now, what is the displacement wave? How the displacement wave will be? It's not a shape of the rope. Why? It's a curve only, not a shape of the rope, like not like a transverse wave. Cos omega, so cos will be three lines. If you want, you can continue. I think one and a half wave is sufficient. I'll make it little bit. Okay, almost we'll compare many particles so that it'll be easy for you. Okay, so this is plus A, this is minus A, this is Y, this is X graph, and the wave is propagating towards right. Now we have, when there is no wave propagation, the particles will be here, this one. We'll donate several particles in what direction they will be moving. But where the particles position, let me show it here. This is not needed. Yeah. And now how to plot the pressure wave. I'll show by the other color. Please, very important, almost all the concept I'm trying to cover using this graph. No, please, you have to understand what all you have doubts. No, everything will be available here. Look at this one. So it's a sine graph, no? It's a sine graph. little bit thick will make it. What is this? There's a pressure I'm plotting. So what is the pressure here? The mean atmospheric pressure is P naught. So how much pressure here? P naught plus BAK. How much of pressure here? There's a pressure. Let me write it. Atmospheric pressure. The pressure at a given point and the wave is propagating the same thing. And this is X. At T equals 0, we have plotted. Okay, now how the different layers will be moving. Okay, what do you mean by compression? Where pressure is maximum, no? Where pressure is more than P naught. So how you categorize compression where pressure is more than P naught? What do you mean by rarefaction? Pressure less than P naught. I think yesterday's in the class we have formulated it. Okay, I'm interested in the layers. So what are the layers? The layers are present here. These are the layers. We'll pick up few layers here. One, two, three, four, five, six. Okay, 15 particles is what I picked up. The very first question, which layer in what direction will be moving? If a layer is plus A, what do you mean by that? It is at a distance of plus A from the mean position. Okay, that one, it is at extreme point, right extreme. If I say the layer is at having a displacement of minus A, so shall I say it is at left extreme? So those layers which are having a maximum displacement plus A, so they are said to be at right extreme. Those layers which are having a maximum displacement of minus A, they are said to be left extreme. And we know if a layer is at executing SHM, if it is at extreme point, what is the state of it? Should be at rest. So which all layers are at rest now? Now you can ask questions. So like a this what again once again. So what about this layer? I'm really coming into the original the discussion what we were supposed to do here now. If a layer what happen is at mean position, it can be moving towards right or towards left. No, it's at mean position moving in the direction of wave. The layer is at right extreme. Here the layer is between mean and the right extreme, and the layer is moving in the direction of wave. What about this layer? It is between mean and the right extreme and moving opposite to the wave, direction of propagation. What about this layer? It is at left extreme. And what about this layer? Between mean and left extreme, moving away from mean position or, or opposite to direction of wave propagation. What about this layer? Between mean and extreme, and moving in the direction of wave propagation. How you measure what is X here? What is X? X is the position of a layer. X from where I'll measure? I'll measure somewhere from the origin. Then what is Y? For a given layer, Y I should measure from its mean position. Are you getting no the Y? So tell me like what is this? It is the shape of the layer or it's a curve? YX graph. Anybody? Because they're the best question a teacher should ask to the student. Not teachers should explain. Teachers should ask for a student. What it is? Is it a shape of the medium at t equal to 0, or it is just a curve? Anybody? Like y-x graph will give the shape of the rope at any time t. Similarly, here y-x graph will give the shape of the medium at any time t. It's a curve. It's not a shape of the medium. It's only a curve. Got the all of you? It's just a curve. It's just a curve. That's all. Finish short. It's a mathematical curve. Okay, we have a formulas. Now, if I differentiate this, the particle velocity is given by A omega sine okay, this is the particle velocity. Then if I differentiate this with respect to dy by dx, or directly I'll write it. What is the expression for particle velocity? Velocity of any point. Again, the same formula is useful for us. Dy by dx. Okay, now. Which all layers are at rest? Instantaneous rest. Shall I say 1, 5, 9? So layers at right extreme. Which are layers at right extreme? 199. Layers at left extreme. 5 and 13. I think there's a better, no, we have a better information. No, again, the layers which are at mean position. I think these will be also at rest, are at rest. Because those which are at extreme should be at rest. No, the layers which are at mean position. Anybody? 3, 7, 11, 15. Okay, good. No, we are in somewhat better position. No. Can we say which layers are moving in the direction of wave? Layers. Moving in the direction of. How to decide? I'll take help of slope. Okay, fine. What is the slope here? Negative. Wave is moving towards left. Okay, there's a wave speed. Okay, I'll change it. Somebody suggested sir like a v wave speed. No. What is the slope at 2, 3, 4? What is the slope at 2, 3, 4? Negative. Negative of negative, positive. So therefore, all these layers are moving towards right. So I will give like this. Layer 2, 3, 4. Let me put dot so that it'll be easy for you. No. So look at the arrows. Let me use. Oh. That me. Let me use this. We have. No, the layers at 2, 3, 4. In what direction they're moving? They're moving in the direction of wave. What about 6, 7, 8? Slope is positive. Wave velocity is positive. So particle velocity negative. Negative means they're moving opposite to that one. So in what direction? They'll be moving in this direction. Arrow not visible properly. I'll increase the size. Okay, somebody is telling sir arrows not visible properly. I'll put once again. See that one. Okay, no, this is clear. No, come for next 6 will be like this. What about 9? 9 will be at rest. Again, 10 will be moving like this. Okay, got the idea? And 13, those layers which are at rest, I'll put dot. Those which are at extreme. Okay, this is what happens here. So layers moving the direction of wave. So what all will put it? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Look at the red color arrows in the direction of wave propagation. 2, 3, 4, 2, 3, 4, 10, 11, 12. 10, 11, 12. Layers moving opposite to the direction of wave propagation. No, looking at the 6, 7, 8, 6, 7, 8, and 14, 15. These are the visible for us. Okay, got the idea now? So how to put this one? Now, sir, you said something compression. What do you mean by compression? Where pressure is more than P naught. That's the compression. Okay, now which all layers are in compression? Where pressure is P naught. So don't look at here. You don't get any help. You should look at here now. So now which all layers where pressure is more than P naught? I think this everything is compression. So 2, 3, 4 are compression. Then again 10, 11, 12 are compression. Don't say 9. 9 is not a compression because what is the pressure at 9? It's P naught, no? So what is the compression? Compression means where pressure is more than P naught. Got the idea? So shall I say this is the compression? Compression. And what is the rarefaction? Rarefaction means this one. There's a meaning of rarefaction. So where pressure is less than P naught. So what is the compression now? Compression will be layers undergoing compression. So 2, 3, 4, 2, 3, 4, 10, 11, 12. Layers are undergoing rarefaction. Which are those layers? 6, 7, 8, 14. Because 15 I cannot take because 15 is mean position. Able to understand this one? So there's a one very quite simplified way, no? No. Which layer is having maximum compression? Layers having maximum compression. Where pressure is maximum, where the pressure is maximum? Here, no? P naught plus BAK, P naught plus BAK, pressure is maximum. So which layers are undergoing maximum compression? 3 and 11. Layers having maximum rarefaction. Which layers? 5 and 15. You can see like and all. So sorry, 7, 7. Pressure is how much? Minimum, no? P naught minus BAK. And again here, P naught minus BAK. So 7 and 15. Slowly, I think now hope you are able to understand. If a sound wave propagates, no, this is what happens here. So the mathematics is helping us to understand the wave propagation. Yesterday, what I discussed, no, it was like a story. The mass will help us know which layer compression, rarefaction, where maximum compression, maximum rarefaction. Yesterday, you might have felt happy. Okay, we understood. No, actually, you understood. Okay, no. So there's a difference for the preparation for advanced. No, when you go for preparation for advanced, no, we will learn everything using maths. Using maths, open will prove everything. Okay, got the idea, no? So now if a sound wave, so usually what are the type of questions? If they ask you displacement, if they give displacement wave, can you say compression rarefaction using displacement wave? Not possible. Huh? So what you should do? So if they give displacement wave, okay, write a wave equation. Then using this formula, bring the pressure wave. Then plot pressure wave, where pressure more than P naught, compression, less than P naught, rarefaction. But looking at here, very dangerous. Am I right? This will be very dangerous. Looking here, looking at this graph, okay, at 2, compression rarefaction. Very difficult. Huh? Let me check it. Okay, 15. 15 is what? Maximum rarefaction, no? Where pressure 5 and 15, you look at this one. Sorry, 7 and 15, what when the pressure is least, okay, maximum rarefaction. What is the problem? Oh, you mean to say here, no? 4 and 15. Okay, then I'll do one thing. 6, 7, 8, 14, 15. It's there, man. Okay, this one. I think I forgot. Yeah, fine. Okay, agreed, all of you. So this is the one method of, now if they give pressure wave, using this, can you tell like a which layer in what direction moving? Very difficult. So what you should do, if they give pressure wave, from the pressure wave, predict the displacement wave, then plot displacement wave. From their slope, you with the help of that, you can predict in which layer, in what direction it is moving. Good idea. What about the layers where pressure is equal to P naught? No compression, no rarefaction. What is that layers? I think it mean no. 1, 5, 9, 13. You look at the pressure. This point. What is the pressure? Equal to mean atmospheric pressure. What is the pressure here? P naught. Pressure P naught. Pressure P naught. Pressure P naught. Okay, got this one. At that instant, the pressure is this P naught here. Okay, now, what about the kinetic energy? Which layer are having maximum kinetic energy? Those which are at mean position, they will have maximum speed, no? Maximum speed, which layers will have maximum kinetic energy? I'm directly maximum speed, those which are at mean position. We know it's executing SHM. So kinetic energy, where it is maximum. This is very important. Layers having maximum kinetic energy. Layers having maximum kinetic energy. K max. Yeah, who will answer? 3, 7, 11, 15. Layers having maximum potential energy. Anybody? Okay, let's come for this one. According to the potential energy concept, where slope is maximum, speed will be maximum. We'll agree. Where slope is maximum, their potential energy also will be maximum. Am I right? Long back we are discussed in the transverse wave on a rope. Where slope is maximum, there also potential energy should be maximum, kinetic energy should be maximum. Again, the same thing, 3, 7, 11, 15 only. Okay, now, will you say that at extreme potential energy maximum? No. At extreme potential maximum, no here. So now you look at this one. At maximum compression or at maximum rarefaction, what will be the potential energy? At maximum compression, 3 is having maximum compression. What is the potential G? Maximum. Kinetic energy will be maximum. Got the idea? At maximum rarefaction, potential G will be maximum. Kinetic energy maximum. These are very important. Layers which are where the pressure is P naught. Then what is that layer? The layer will be at extreme. So kinetic energy should be zero. Potential energy also will be zero. If a sound wave propagates where the pressure is the layer which is having maximum compression, what happens to their potential energy? Or better, we call this a strain energy. Strain energy will be maximum. Kinetic energy will be maximum. What about the kinetic energy of the layers where the pressure in compression? As I move from P naught to P naught plus BK, there's a compression, no? As I move from mean atmospheric pressure to maximum compression, here like this, what will happen to kinetic energy? Will increase, no? Will agree? Here you can see kinetic energy here will be zero. It increases, it becomes maximum. So if compression increases, then what happens to kinetic energy will also increase. Potential energy also will increase. If compression decreases, potential energy also, kinetic energy decreases, potential energy decreases. And here at mean atmospheric pressure, both potential kinetic will be zero. So shall we put like this here? The one best conclusion is what I wanted to make it here. Where is the blue color one? Some other. Let me take this one. No. So shall we put here U max, K max, U minimum, K minimum. Here U max, K max. What about here? U minimum, K minimum. Got the idea? This one. So again, will the layer will move vertically up and down? No, the layers will move horizontally. Very important, the arrows. What is this? There's a curve. It's not a shape of the curve. What is this? This again, the variation of pressure, no? So these two are curves. They're not shape of the medium, not like a transverse wave. Okay, got the idea, no? So this I took. So now they'll plot this for sine graph. Okay, let's see one more so that you'll get exact picture.